Triv, you ready? You ready? You ready? I'm really excited.
Oh, I can tell. That's an amazing outfit. What? Ready for what?
Well, the taxi's going to be here in a few minutes, so we're going to be ready to go.
Ready to go to... But where are we going, mate?
The concert, remember the concert?
The concert to see who?
Equilibrium. Remember you emailed me, you said, next week, remember, Jill's house, we're going to do Equilibrium... Oh.
I think you misread it, Wayne, because I said the equilibrium constant.
Yeah. I've worked that out now, that makes more sense.
So did you say you booked a taxi to...
Yeah, in a few minutes, it's just going to take us to London.
To London?
Yeah.
Oh. Better go on to this then, really.
Yeah, we should.
Oh. There is no concert though, Wayne. You're already ready for that. Anyway.
You ready?
Yeah.
Good.
So the equilibrium constant is a constant.
It is.
And it's to do with equilibrium.
It is indeed. Well done, you.
Thank you. So there's lots of constants in A2 chemistry. This one is Kc, that's how you denote it, and it's the products over the reactants.
Indeed.
So it's all about equilibrium. So what Wayne's doing now is he's writing up like a stock reaction for equilibrium, where the lowercase letters denote the molar value, so the stoichiometry things, and the other things, the concentrations of each species in the reaction.
And then I've wrote what Triv was just saying about products over reactants being the Kc.
Yeah. The products are always moles per decimeter cubed. No seconds here, so it could have no units.
It could have no units.
Could just be another one here.
So, if we have an example of a reaction that takes place, hydrogen plus iodine gives 2, that's reversible, like that. Hydrogen iodide, 2.
Okay, so we want to work out the equilibrium constant, so we have put these into the equation. These are our products, but as it's a 2 in front of the HI,
it's second order.
Yeah.
These two are both first order, and it's also worth mentioning all of these are gaseous, they're all in the same state, which makes it a homogeneous, or genus, equilibrium. They're all the same state. So if they were different states, it would be heterogeneous. Can't
Just
say
like
it, but
that.
I can spell it, that's what counts.
that's the important thing, it's a heterogeneous, homogeneous state things.
The generic drawing for equilibrium on a graph.
We have the concentration of the reactants, well that's the product, the concentration of reactants decreases and the concentration of the products increases.
When they level off.
That is your equilibrium point.
Exactly.
Yeah.
And that looks the same for all of them. For this one you've got hydrogen and iodine, so they're represented by this line.
Yeah.
You start with lots of them and 0 products, so that's what they look like.
So, these are the things. So if we then go through an example.
Yep, some examples, they just give you the concentrations and you just plonk them into the formula and you get a value for Kc and then you have to work out the units.
Yeah.
They do sometimes do things slightly more jazzy.
Sometimes they just give you a table of a few values and you have to work out the rest of by sort of semi-logicking out what part they want.
So if we stick with our nice example here, we've got hydrogen plus iodine and hydrogen iodine, you've got the conc at the start.
And then concentration at equilibrium, they'll always give you this bit. And they'll probably give you all the concentrations at the start, or maybe at least some of them. Enough to work it out.
Yep. In this case, the one that is in the book that we've read this is 0.6, this is 0.4, these are all moles per decimeter cubed.
Alright.
And this is 0 because you haven't at the start of the reaction, you haven't made any product.
Alright.
And the only thing extra they've told you is that at the end, they've made 0.28 moles per decimeter cubed of hydrogen. It asks you to work out Kc. Now you might be looking at that thinking, what? You don't have enough values.
Yeah. You can work out the values. As your concentration of hydrogen has gone down by 0.32,
Yep.
that must be changed into something.
If we write up the reaction I've just rubbed out, because I was silly.
This is a reaction that we've undergone, so having an equilibrium reaction of hydrogen and iodine forming hydrogen iodide.
So then, as Triv just said, this is 0.32. Because of stoichiometry, this must have been 0.32, and this must have been double that at 0.64 as amount produced and amount reacted.
Yeah, so that means we have our amount reacted here.
Yeah, that must be 0.64. But this isn't 0.32.
Because it's been 0.32.
That's the amount that has been reacted, so the
Yeah.
amount left would
Must
be
be
0.4 minus 0.32.
Yeah, which is 0.08.
Exactly. which can be quite tricky to get your head around. So far I've only seen one question like this on an exam,
Yeah.
but it does come up.
And once you've sorted that bit out, then you can go on as normal,
Yeah.
putting it into your values. So we can do that.
Yeah, so we're working out KC is the ultimate question, don't forget that when
Yeah.
you're doing all of this.
So you have products every reactance, products is your HI. So you have our
And it's second order, don't forget. So
Yeah.
it's 0.64 squared divided by 0.28 times 0.08. Now, you'll have a calculator, you'll do that as a sum. The important part is the units.
Yeah. There we go. That answer.
Yeah.
But this is one of the cases where there'll be no units at all.
Moles per decimeter cubed is squared on the top, so there's two of them.
Yeah, and then
And
one
there's
of
two
each.
on the bottom.
So these will cancel entirely to 1, so I'll have no units for this reaction, which does seem like a bit of an odd thing to have.
It does, it does. And that's it so far. In the next video, if you want to look at the equilibrium constant as a whole thing, check out the next video.
Yeah, we'll talk about how it's affected by temperature and other factors.
And for now, our taxi's arrived and I've paid for that. So
I better go to London. Let's go to the museum.
I love it.